Alright guys, welcome to your third video on applications of derivatives. In this lecture we're going to focus on finding equations of tangent lines, determining increasing, decreasing intervals of a function, finding local maximums and minimums of functions, and then also talk about concavity. Okay, so the first thing we want to talk about are tangent lines and how to find the equation of a line tangent to a graph of a function f. This is probably the most basic application of the first derivative because the derivative is known as what's called a slope generator, which basically means that if you plug in a value of x to the derivative, what you get back in return is the slope of the tangent line to the graph of f of x, which is the original function, at that particular value of x. Okay, so example 1, letter A here, we have this function and we want to find the line tangent to the graph of f at x equals to 2. In order to find that, I've got to first of all find two things. The first thing is I have to find a point. Well, the problem already gave me half of an ordered pair. They tell me that they want the equation at x equals to 2, and so that is my x coordinate. In order to find the y coordinate, I'm going to do what I did in Algebra 1. I'm going to take x and I'm going to substitute it into the function. So that's going to say f of 2, which is going to be 2 squared multiplied by 2 minus 3 squared. And if you do the arithmetic there, you're going to get 4. So what this means is that my equation for the tangent line passes through the ordered pair 2, 4. The second thing that I need in order to write my equation of a tangent line is a slope. And this is where the derivative and the calculus part of the problem comes in. So in order to find this derivative, f prime of x, if you notice, this original function is a product, and so what I'm going to have to utilize is the product rule. Okay, so the product rule says the first multiplied by the derivative of the second. The second is x minus 3 squared. So I bring the 2 into the front. I rewrite x minus 3 to the first power and then multiply by the derivative of x minus 3, which is 1. Plus the second, so I write down x minus 3 squared, multiplied by the derivative of the first, and the derivative of x squared is just 2x. Now, if I was going for the derivative on this problem, I would probably do some algebra to clean this up. But since the only thing I'm really worried about is the slope, I'm just going to go ahead and substitute in here and then try to figure out what the value is. So f prime of 2 is going to equal, I'm going to substitute a 2 in for that x and then square it, multiplied by 2 times 2 minus 3 times 1 plus 2 minus 3 squared times 2 times 2. Okay, so if I clean that up, 2 squared is 4 times 2 times negative 1 times 1 plus 2 minus 3 is negative 1, so I square it, and then I multiply by 4. And so this is going to equal to 4 times 2, which is 8, times negative 1 is negative 8, plus negative 1 squared is just positive 1, and then times 4 is 4. Negative 8 plus 4, of course, is negative 4. Okay, so there is my slope. This right here is my slope of my tangent line, and so now I'm ready to write the answer. So I'm going to use the point slope form of a line, which says y minus y1 is equal to m times x minus x1. And so I have y minus y1. Well, y1 was right there. It was the 4. So y minus 4 is equal to the slope, which was negative 4, times x minus x1, which was 2. And when you write the final answer, I just want you to have it where y is by itself. So in order to do that, I'm going to add 4 to both sides and get y is equal to 4 minus 4 times x minus 2. Okay, and the reason that I have you write it in that form will become more obvious later on when we get to class, and I can actually explain that to you, and you can see why we do it that way. Okay, example B, we have f of x is equal to sine x minus cosine x, and we want to write the equation of the tangent line at x equals to pi. Okay, so very similar to the first problem, we want to first of all find our point, and so that's going to require us to plug pi in for the original equation. So f of pi is going to be sine pi minus cosine of pi, which is equal to, sine of pi is 0, minus the cosine of pi, which is -1, and 0 minus -1 is +1. And so that means that my point is going to be pi, comma 1. The second thing that we need, of course, is the slope, and in order to get the slope, we need to take the derivative. So f prime of x is going to equal to the derivative of sine of x, which is cosine x, minus the derivative of cosine x. Well, the derivative of cosine x is negative sine x, and since there's already a negative in front of that, this is going to jump back to positive. Okay, so now if I plug in pi to the derivative, that's going to give me my slope. So cosine of pi plus the sine of pi, which is going to equal to -1 plus 0, which is equal to -1. Okay, so that means that my equation is going to be y equals to y1, which was 1, minus the slope. Okay, usually it would be plus the slope, but because the slope is 1, I'm going to put -1 multiplied by x minus pi. Now, obviously, you don't need the 1 right there, so if you wanted to erase that, you definitely could. Okay, and so you would just have 1 minus x minus pi. Okay, so the second thing we want to talk about are critical points and increasing, decreasing intervals. And this is where I really think calculus gets fun and exciting and really shows its power, is in the ability to determine when is a function increasing or decreasing and where does a function have maximums and minimums. Okay, so very important definition here, so I'm going to highlight it. Definition: let f be defined at c if f prime of c is equal to 0, or if f prime of c is undefined, then c is called a critical point of f. And sometimes we call these also critical numbers. Okay, so critical numbers, some textbooks will use that terminology as well. Okay, so example 2, we want to find the critical points of the function. So f of x is equal to 1/3 x cubed minus 2 natural log of x. Well, in order to find critical points, I have to take the first derivative. So f prime of x is going to equal to x squared minus 2 times the derivative of natural log of x. Remember that the rule is u prime over u. In this case, u is just x, and so the derivative is 1 over x. Okay, well that will clean up to x squared minus 2 over x. Now remember, critical points come whenever the derivative is equal to 0, so in a minute I'm going to set it equal to 0. Or when the derivative is undefined. And what you should notice here is that there is a denominator for this derivative right there. So basically, in order to determine where f prime is undefined, we need to figure out where is that denominator equal to 0. Well, if I set that denominator x equal to 0, I get my first critical point, which is just x equals to 0. Okay, so that's my first critical point. I'm going to highlight it in yellow so that you know it came from the fact that the derivative was undefined at that point. Okay, the next thing we want to do is set this equal to 0 and go ahead and solve for x. So if I move over the 2 over x term and then multiply both sides by x, what I'm going to be getting is x cubed is equal to 2. And to get x by itself, I'm just going to take the cube root of both sides. So x is going to equal to the cube root of 2, and that's going to be my other critical point. And that critical point came from the fact that the derivative was equal to 0. Okay, so make sure that you are checking both. You need to make sure that your derivative is defined, and if it's not defined, then that particular value is called a critical point. Okay, example B, we have x squared plus 1 times e to the x, so this is going to be a product rule in order to find its derivative. So f prime of x is going to equal to the first multiplied by the derivative of the second. The derivative of e to the x is just e to the x, plus the second, e to the x, multiplied by the derivative of the first, which is 2x. So, sorry about that. Let me erase that and put here 2x. Okay, if I factor out an e to the x, then this is going to say x squared plus 2x plus 1, and I'm going to set that equal to 0. Notice there aren't any denominators going on in this derivative, and so we're not going to have any critical points for which the derivative is undefined. Okay, if I go ahead and factor the parentheses, then that's going to say x plus 1 squared, and I'll let you verify that on your own. And we still want that to be equal to 0. So what we do is we take e to the x and set it equal to 0, and also x plus 1 squared and set it equal to 0. Well, that's going to give me x is equal to negative 1 right there. And e to the x equals to 0 doesn't give me anything, because if I were to take the natural log of both sides, I'm going to get x is equal to the natural log of 0, and the natural log of 0 does not exist. And so because of that, we don't get any critical points from this part. We only get our critical points from x equals to negative 1, which was this part right here. Okay, so because the first derivative represents the slope of a function, it is able to tell us whether a function is increasing or decreasing on a particular interval. So that's what this theorem 3.5 says, is that if f prime is greater than 0, another way to say that is if f prime is positive, then f is increasing. And that should make sense to you, because if f prime is positive, that means the slope of the tangent line is positive, and so that means that the function should be increasing. Secondly, if f prime is less than 0, or we could also say negative in that case, for all x in AB, then f is decreasing on AB, and that should also hopefully make some sense to you, since a negative tangent line would look something like that, and that would mean that the function is decreasing. Okay, so this picture kind of represents what's going on here and kind of shows you how the derivative is related to the slope of a function. Okay, so this leads to another just incredible idea that we get from calculus, and it's called the first derivative test. So let C be a critical point of a function f that is continuous on an open interval that contains that critical point. If f prime of x changes from negative to positive, and another way to say that is if f prime changes from negative to positive, that means that f changes from decreasing to increasing. And I know that if a function changes from decreasing to increasing, then I'm going to get a relative minimum. Obviously, I drew the wrong thing there, so I'm going to erase that and draw what I meant to draw, which is go from decreasing to increasing, which creates my minimum. Okay, similarly in number 2, if f prime changes from positive to negative, what that means is that f changes from increasing to decreasing, and what that does is it creates a maximum point. Okay, so hopefully that makes some sense to you. It's a really intuitive thing that I think makes a lot of sense once you kind of understand what exactly this is saying. Okay, and then thirdly, it says if f prime is positive on both sides of C or negative on both sides of C, then f of C is neither a relative max or a min. And so really what that's saying is that if f prime does not change signs, then we do not have a max or a min. So f prime doesn't change signs, then what that means is that we have neither a max nor a min. Okay, so example 3, we want to find the intervals where f is increasing and decreasing, and then also find the local maximums and minimums. So letter A here, we have f of x is equal to 300x minus x cubed. So the first thing we need to do is find our critical points. That will come from taking the derivative and looking to see where is it undefined or where is it equal to 0. So the derivative of this function is going to be 300 minus 3x squared. Well, that's just a polynomial with no denominators going on, and so because of that, this derivative is going to be defined for all real numbers, and so I don't have any critical points where the derivative is undefined. But if I set it equal to 0, I am going to get a couple of critical points. Okay, so what I'm going to do is I'm going to factor out a 3 from both of the terms here, so that's going to leave me with 100 minus x squared equals to 0. And then what I notice in the parentheses is that that's a difference of squares. So this is going to be 3 multiplied by 10 minus x times 10 plus x. Okay, and what that does is it really helps me to see what exactly the critical points are. I can now see that the critical points are 10 and negative 10. Okay, so what I'm going to do with those points, because I'm not sure if they're maxes or mins yet, I'm going to put them on a number line and then test intervals to see if the derivative is positive and negative in those sections. Okay, so here's negative 10 and positive 10, and what I'm going to do is I'm going to check numbers from each interval here to determine if the derivative is positive or negative. Okay, so in this first section, I could try negative 11, or really anything that's less than negative 10. And if I plug negative 11 in for x, I'm going to do it in the factored form, this factored form right here of the derivative. That's going to make it easier for me to determine what the sign is. Because remember, I don't really care what the value is. I really just care, is it positive or negative? Okay, so if I plug in negative 11, 10 minus negative 11 is a positive, 10 plus negative 11 is a negative, and a positive times a negative is a negative. And so in this section, the function is going to be decreasing because f prime was less than 0 or negative. Okay, in the second section, we could choose 0. That's typically the value that I'm going to choose just to make things easy on myself. So if I plug in 0 for x, 10 minus 0 is positive, and 10 plus 0 is also positive, and two positives are going to make a positive. Okay, and then for anything greater than 10, we could certainly plug in 11. And if we plug in 11, then 10 minus 11 is negative, 10 plus 11 is positive, and a negative times a positive is negative. Okay, so this is now going to allow me to write my answer. So I'm going to write down that this function was increasing on the interval from negative 10 to 10. It was decreasing from negative infinity to negative 10, and also from 10 to infinity. And then I also have one max and one min. So I have a max wherever the derivative went from positive to negative, and that would be at x equals to 10. Okay, and if you notice the chart, it really kind of helps you determine where the maximums are, because you can see here the derivative went from the function went from increasing to decreasing, and so that's how we had a maximum created right here at this point. So this was a max. Okay, and then similarly, we're going to have a min at x equals to negative 10. For the opposite reason, the function went from decreasing to increasing here, which created a minimum at x equals to 10. Okay, example B, g of x is equal to 1/3 x cubed plus 3/2 x squared minus 70x plus 5. I'm going to work through this one a little more quickly, only because it's very similar to example A. So the derivative is going to be x squared plus 3x minus 70. Again, there's no denominator here, so I just need to set it equal to 0 to find my critical points. And if I factor this, I need factors of negative 70 that add to 3, and that would be x plus 10 and x minus 7. Okay, so that's going to give me the critical points, x equals to positive 7 and negative 10. I'm going to put those on a number line, so negative 10 is going to go here, positive 7 will go here. Okay, in the first section, if I want to plug in negative 11, the first factor of the derivative is going to be negative. The second factor is also going to be negative. And so a negative times a negative will give me a positive. In between negative 10 and 7, I could choose 0. If I plug in 0 to both of those, I'm going to get a positive times a negative, which of course is a negative. And then after 7, I could plug in 8. And if I plug in 8 to both of those, they're both going to be positive. Okay, so this function is increasing on the intervals from negative infinity to negative 10, and also from 7 to infinity. It is decreasing in the middle there from negative 10 to positive 7. We have a maximum point wherever the derivative went from positive to negative, and that would be at x equals to negative 10, and a minimum, in this case, at x equals to 7. Okay, the next application of the derivatives that we want to talk about is concavity. So concavity and points of inflection are information about a function that is told to us by the second derivative. So when we work these problems, we're going to have to find the second derivative and use that to get the information about concavity. So let's start with these two important definitions of concavity. It says, let f be differentiable on an open interval. The graph is concave up whenever f prime is increasing and concave down whenever f prime is decreasing. So that is the definition of concavity. Okay, and then secondly, what I want you to see is that if a graph is concave up, what that means is that the tangent lines are all below the function. Okay, so I'll show you the picture here in just a second to kind of illustrate that. Secondly, if the graph of f is concave down, then the tangent lines are above the function. Okay, so if you look at this picture, that's kind of what this picture is saying. This first graph here is concave up, and you can see that f prime is increasing because if you were to look at this slope right here is a negative slope, and then the slopes become positive. So this is a positive slope. This slope is also positive, and it is a greater slope than this second slope right here. This third one is bigger, and so f prime is increasing. And you can also notice that the graph lies above its tangent lines, or really another way to say that is that the tangent lines are below the function. Okay, similarly here for concave down, so this is a concave down graph. You can see that f prime is decreasing because we started off with a positive slope here, and then we're getting negative slopes here and here, and the slopes are getting more negative as you go along the function. Okay, and also notice that those tangent lines are above the graph, and so that's what makes the graph concave down. Okay, so the test for concavity, we're going to use the second derivative, and we're going to determine where it's positive or negative. So if f double prime is greater than 0, which also means positive, that means that the graph of f is concave up. If f double prime is less than 0, or also negative, is what that means, then the graph of f is concave down. And a point of inflection is whenever a graph changes concavity, either from concave up to concave down, so concave up to concave down, or concave down to concave up. Okay, so that's one of the cases where a function has a point of inflection. The second is when f prime changes from increasing to decreasing or decreasing to increasing, and that just follows from the definition back up here that a graph is concave up when f prime is increasing and concave down when f prime is decreasing. And then the third is f double prime changes from positive to negative or negative to positive. Okay, so what we're going to do now at the bottom of page 4 is kind of summarize all of these theorems and definitions that we've talked about. So in this first column, I'm going to write down f along with its first two derivatives, f prime and f double prime. Okay, well, we learned on page 2 that if f is increasing, f prime is positive, and if f is decreasing, f prime is negative. Now that same information will translate down a level whenever we talk about f prime. What that means is that if f prime is increasing, it means that f double prime is positive, and if f prime is decreasing, then f double prime is negative. Okay, and then by definition, back up at the top of page 4, if f prime is increasing, that means that f is concave up, and so I'm going to draw a graph that looks concave up, and if f prime is decreasing, then f is concave down. This is a chart that you need to be able to recreate on your own. Okay, a lot of the times, if you can redraw this chart on a question, you're going to be able to answer the question pretty easily. And so I would just go ahead and encourage you to have this chart memorized, and so that way you can reproduce it on any question. Okay, so in order to check intervals of concavity, even points of inflection, it is always easiest just to look at the second derivative if you're not, if you don't have a calculator or if you're not looking at a graph. So example 4, find the intervals of concavity and the points of inflection. Okay, so example A, we have this function. We're going to take the first derivative, which is going to say 3x to the 4th minus 12x cubed. And so that means that the second derivative is equal to 12x cubed minus 36x squared. And remember, I'm taking the second derivative because the question is asking me about concavity. Okay, so this is going to equal to 0. I'm going to go ahead and factor out what can be factored out. And in this case, that's a 12x squared. And that's going to leave me with an x minus 3 equals to 0. Okay, so if I set both of those factors equal to 0, I'm going to get x equals to 0 and x equals to 3. And these are what are called my possible points of inflection. And the reason they are possible points of inflection is because I have to actually test whether or not they are points of inflection by seeing if there is a sign change in the second derivative. Okay, so we're going to put 0 here and 3 here. And so if I plug in -1 to the factored version of the derivative, which is right here, that's what I'm going to plug into, is the factored version, then 12 times -1 squared is positive, and then -1 minus 3 is negative. So a positive times a negative is a negative, and so I'm going to draw concave down in that section, since if the second derivative is negative, that means that the function is concave down. Okay, in the middle section, I could plug in either 1 or 2. Either one would be fine. If I plug in 1 for x, then 12 times 1 squared is positive, and 1 minus 3 is negative. And so again, between 0 and 3, the function is going to be concave down. And so what you should notice right now is that x equals to 0 was a possible point of inflection, but it is not an actual point of inflection since the second derivative did not change signs, which means that the original function did not change concavity. Okay, and then in the last section, we could plug in 4 for x into the second derivative. 12 times 4 squared is positive, and 4 minus 3 is also positive, and so the function is going to be concave up there. Okay, so I'm going to use that chart to now write my answer. This function is concave up on the interval from 3 to infinity. It is concave down from -infinity all the way to 3. And we did skip 0 here and just included it in our interval for concave down. If that confuses you or you don't feel okay about that, then please feel free to contact me and I'll explain that in more detail. But just take my word for it, we are going to include 0 in that interval. Okay, and then there is a point of inflection going on at x equals to 3 since there was a change in the sign of the second derivative. Okay, example B is a similar problem, although it has trig in it, so we're going to have to remember our trig values and some things about the unit circle. So if I first of all take the first derivative, f prime of x is equal to cosine x, and then the derivative of cosine x is going to be negative sine x. And then the second derivative, f double prime, is going to equal to the derivative of cosine is negative sine x minus the derivative of sine, which is cosine. Okay, so if I set this equal to 0 to find my possible points of inflection, I'm going to get negative sine x is equal to cosine x. This is a problem that you should have solved in the first assignment over the unit circle. And so if you'll recall, you should have gotten x is equal to 3 pi over 4 and also 7 pi over 4. Okay, so if we put those on a number line, we can test concavity in these intervals. So 7 pi over 4 will go there, 3 pi over 4 on the left. Okay, well, I'm going to try to keep this to being things that are on an axis because I know the values of those are either 0, 1, or -1. And so it's going to be easy for me to compare whenever plugging into the second derivative. And remember, into the second derivative is going to be into this function right here. Okay, so from 0 to 3 pi over 4, pi over 2 is in that interval. So I'm going to plug in pi over 2 to the second derivative. So I'm going to end up having negative sine of pi over 2 minus the cosine of pi over 2. Well, sine of pi over 2 is positive 1. So this is going to be -1 minus the cosine of pi over 2, which is 0. And so -1 minus 0 is -1, which means that in this interval, the function is concave down. Okay, in between 3 pi over 4 and 7 pi over 4, I know is 4 pi over 4, or better known as pi, and so I'm going to plug in pi for that interval. So negative sine of pi minus the cosine of pi. Well, sine of pi is 0 minus the cosine of pi, which is -1, and 0 minus -1 is equal to +1. And so in this interval, the function is going to be concave up. And then in the final interval, I'm not going to be able to do anything that's on an axis, but I could plug in perhaps 11 pi over 6 if I wanted to. So if I plug in 11 pi over 6 into the second derivative, that's going to be negative sine of 11 pi over 6 minus the cosine of 11 pi over 6. Now again, I don't really care about the value necessarily, I just care about the sign. So let's see if we can figure out what this is. This is going to be negative of sine of 11 pi over 6, which is negative 1/2, minus the cosine of 11 pi over 6, which is positive square root of 3 over 2. So what I end up getting here is positive 1/2 minus the square root of 3 over 2. Well, since square root of 3 over 2 is bigger than 1/2, I'm subtracting a bigger number, which means that this is going to be negative. And so in this interval, we are going to be concave down. Okay, so we are now ready to write our answer. This function was concave up on the interval from 3 pi over 4 to 7 pi over 4. The function was concave down on the intervals from 0 to 3 pi over 4, and also from 7 pi over 4 to 2 pi. And the reason I'm using 0 and 2 pi there is if you go back up and look at the problem, the interval that we cared about here was from 0 to 2 pi, and so I'm not going to put negative infinity or positive infinity. And then there were points at, whoops, let me go back to the pen here, not the highlighter. There are points of inflection wherever the second derivative changed signs, which would have been at x equals to 3 pi over 4 and also 7 pi over 4. Okay, so the last thing we're going to do in this lecture is use our chart that we did on page 3, I believe it was, and might have been page 4, and we're going to answer some questions using the graph of f prime. So the first thing I'm going to do is I'm just going to recreate that chart that we did on one of the previous pages. Okay, so I know that if f is increasing or decreasing, then f prime is positive or negative. That information translates down a level, so increasing, decreasing, positive, negative, and by definition, this means concave up, and that means concave down. Okay, so part 1 of example 5, it says to find all critical points of f and classify them each as a local max, local min, or neither. Okay, well I know from the definition on page 2 that critical points come whenever the derivative f prime is equal to 0. And remember, back up there it says that we're given the graph of f prime, and so that's what we're looking at when we look at this graph. Okay, so if we look at all the places where f prime is equal to 0, that's going to be here, 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 and there. Okay, so we have 4 critical points, and I'm going to write those down sort of in a linear fashion so that I can write a sentence out next to them that describes what type of critical point they are, whether it's a max, a min, or neither. So we have x equals to -2, +2, 6, and 10. Okay, well at x equals to -2, what you should hopefully notice is that the derivative graph is changing from negative to positive. And so if I look back up at my chart, if f prime changes from negative to positive, that means that the original function changes from decreasing to increasing, which is going to create a minimum. Okay, so I'm going to write x equals to -2 is a local min. And then in order to justify my answer, I'm going to say because f prime changes from negative to positive. Now, I have to be very specific here in saying f prime. It's not okay for me just to say it or the graph or even the given graph. We have to say f prime changes from negative to positive. I always want to make my argument based on what I am given. Okay, at x equals to 2, that's the next critical point, I see that there is no sign change in the derivative. The derivative is positive before 2 and then positive after 2, and so x equals to 2 is neither a max or a min, and I don't really need to say that part. I can just say neither, because f prime does not change signs. Okay, so that is the justification on why x equals to 2 is neither a max nor a min. Okay, at x equals to 6, I see the opposite happening of what I saw at x equals to negative 2. I see the derivative going from above the axis, or positive, to below the axis, or negative. So at x equals to 6 is going to be a local max because the derivative graph, f prime, changes from positive to negative. Okay, so that is a well-constructed sentence that correctly justifies my answer. Okay, and then at x equals to 10, I also see what was going on at x equals to 2. There is not a sign change in the derivative, so I'm going to say that x equals to 10 is neither, because f prime does not change signs. Okay, so that completes number 1, so now we can move on to number 2. We want to find all intervals on which f is increasing or decreasing. Okay, so number 2 here, we want to say increasing, and we want to try to figure out when that's going to be. Well, if I look at my chart, f is going to be increasing whenever f prime is positive. And whenever I'm looking at a graph, positive just means above the x-axis. So positive would be all of this right here. Okay, so if I go down and write that, increasing, that would be from negative 2 to 6, and the justification is because f prime is positive. Okay, and then I want to say, when is f decreasing? Well, f is decreasing whenever f prime is negative, and that's what you can see right here from the chart. And so that's going to be here and also in those sections. Okay, so I'm going to write down from negative 4 to negative 2, and also from 6 to 12. And again, the justification is going to be since f prime is negative. Remember, you want to always argue through what you are given. We are given f prime, and so that's how I need to argue my stance on that particular part of the problem. Okay, number 3 is asking me about concavity. So find all intervals on which the graph of f is concave up or concave down. So I'm going to erase these colors here so that we can do that part. And so basically what we're wanting to see here is that if f is concave up, then that means that f prime is increasing. Okay, so where is f prime increasing? Well, that's, to put it simply, that's wherever the graph of f prime is going up. So that would be from negative 4 to 0 here, from 2 to 4 here, and then also from 8 to 10. Okay, and then where is the graph of f concave down? Well, that would be wherever the derivative is decreasing, and so that's going to be every other part here, which is from 0 to 2, and from 4 to 8, and from 10 to 12. Okay, so if we go down and write that, we are going to be concave up on negative 4 to 0, and also from 2 to 4, and then also from 8 to 10, and that's going to be because f prime is increasing. We're going to be concave down on all of the green parts up there, which would be from 0 to 2, and also from 4 to 8, and then finally from 10 to 12, and the justification there is because f prime is decreasing. And you can feel free to abbreviate increasing, decreasing, positive, negative, however much you want. Okay, scrolling back up to see what number 4 says. Number 4 is find all points of inflection of f. Well, if I go back to the other screen just real quick, we said right here that we find points of inflection whenever f changes concavity f prime changes from increasing to decreasing, or when f double prime changes from positive to negative. So what I'm talking about are these 3 points right here. Well, the argument here is going to be through f prime. The reason for that is because that is what we are given. We are given the graph of f prime. So I'm going to need to try to figure out where is f prime going from increasing to decreasing, or vice versa. Okay, so that's going to happen right here at 4, or I'm sorry, at 0, because I want to do x values. So at 0, at 2, at 4, at 8, and also at 10. Okay, so 0, 2, 4, 8, and 10 are going to be my points of inflection. X equals to 0, 2, 4, 8, and 10. And the justification is since f prime changes from, I don't want to say positive to negative this time, I want to say increasing to decreasing, or vice versa. Okay, so hopefully these problems have helped you remember some things from pre-cal, and now you're able to tackle the assignment. Good luck to you guys. Let me know if you have any questions, and we'll talk to you on the next video.